Annenberg Media.
Está temblando un poquitito. No se asusten, vamos a quedarnos. Les doy la hora. 7 de la mañana, Chihuahua. 7 de la mañana, 19 minutos 42 segundos, tiempo del centro de México. Sigue temblando un poquitito, pero pues vamos a tomarlo con una gran tranquilidad. Vamos a esperar un segundo para poder hablar.
Historian Will Durant once observed that civilization exists by geological consent, subject to change without notice. Durant may not have had earthquakes specifically in mind when he made that statement, but it is difficult to imagine a more cataclysmic event than a major earthquake. Ancient mythology held that tremors occurred due to the movements of giant animals beneath the earth. While science has since proved such notions incorrect, these myths did contain at least one element of truth. The cause for the abruptly shifting land does reside deep below our feet. But instead of the land sitting on a mythological beast, we ride atop a gigantic heat-transporting machine that keeps deep rock flowing and churning. Radioactive decay generates the heat energy which ultimately powers movements of Earth's rocky tectonic plates. The friction between the rough edges of these slowly moving segments of the Earth's lithosphere results in a series of jerky starts and stops, which is the direct cause of most major earthquakes. The same heat engine that produces earthquakes is the driving force raising the world's great mountain ranges. If this uplift did not take place, the relentless force of erosion would reduce the Earth's landscape to a single flat plain. Without the present range of elevations, rivers would lose their principal sources of water. The land would ultimately erode down to tide level, and most of the diversity in the world's flora and fauna would disappear. And yet, while there are indirect benefits to living in a world with earthquakes, it's the capacity of tremors to violently disrupt human activity that commands our attention.
Earthquakes often occur here, on the San Andreas Fault in California. This fault is actually the boundary between two tectonic plates, the North American and Pacific plates. In 1857, this segment of the San Andreas caused a massive earthquake. The ground on either side of the fault shifted suddenly and violently, moving as much as 4 meters. Instruments to measure the strength of the quake didn't exist at the time, but estimates based on eyewitness accounts of the damage range as high as 8.2 on the Richter scale. Since then, California has experienced several devastating earthquakes. In fact, thousands of earthquakes on hundreds of different faults shake California each year. But earthquakes are not just a California story. They occur throughout the world. In regions that are densely populated and where construction practices are primitive, the destruction and loss of life from a powerful earthquake can be almost incomprehensible. In 1990, 50,000 people died in Iran. The year before, 25,000 people were killed in Armenia. And in China, hundreds of thousands of people were killed in a single earthquake in 1976. Earthquakes are shock waves. They are produced when rocks break and vibrate when two blocks of the Earth's crust slide past one another. This usually occurs along a fault, which is a zone of weakness in the Earth's crust. Movement of the Earth's crust causes stress to accumulate in the rocks of the fault zone. I can feel the stress accumulating in my hands as I try to slide them past one another. The rocks will eventually break when the accumulated stress exceeds the strength of the rocks in the fault. The movement of the tectonic plates is the principal source of stress in the Earth's crust. The stress that accumulates over hundreds or even thousands of years is released in an instant as an earthquake. Geologists study the mechanics of earthquake behavior in order to develop an understanding of where and when earthquakes are most likely to happen.
Most of the energy in an earthquake is expended when blocks of rock move into new positions. The energy fractures the rock, forming a plane of slip called a fault, along which future earthquakes can also occur. Some energy generates frictional heat, and a small part of the energy released creates seismic waves.
18 inches again.
These waves can be categorized according to the form they take and the speed at which they travel.
Those that travel in such a way that the matter through which the waves are traveling are alternately compressed and dilated. These are called P waves. The reason they're called P waves is because these are the first ones, the primary waves, to arrive at a seismograph. S waves, which are sometimes called secondary waves or shear waves, are waves which travel by a wave-like motion where the matter is vibrating up and down at right angles to the direction that the wave energy is being propagated. This causes a shear stress to develop in the rocks through which it's traveled, why they're called shear waves or S waves. The S waves travel somewhat slower than the P waves, with a difference in speed about 2 kilometers a second.
This difference in velocity between P and S waves is highly significant. It enables seismologists to calculate the precise location where an earthquake has occurred.
If one lies close to the epicenter of an earthquake, the P and the S waves will not have had enough time really to become separate from one another as they travel through the earth. They arrive all at once, and the earthquake is felt as a sharp jolt. If, however, one lies at a great distance from the epicenter, the P waves will have far outraced the S waves and so arrive much earlier than the S waves do. The time interval between the arrival of the P and the S waves thus is a function of the distance to the source, the epicenter. Having a single seismograph record showing the time interval between the arrival of S and P waves is not adequate for locating the epicenter. It simply tells one how far away the earthquake occurred. The direction is still missing from this information. In order to determine that direction, one examines seismograph records from other stations in the regions as well. One can pull out a map and easily locate the epicenter by drawing circles around each respective seismic station, representing the distance inferred to the source of the earthquake based on the time interval between S and P waves. And where these circles intersect, bingo, that's your source. That's where the earthquake energy first reached the Earth's surface.
In the 2nd century, the Chinese built a device that could detect the initial ground motion during an earthquake. It consisted of 8 metal balls arranged around the circumference of a large sphere. If the Earth shook hard enough, a small pendulum inside the sphere swung back and forth, knocking one of the balls off its stand. This indicated the direction that the earthquake vibrations came from. At the turn of the century, a more advanced device was designed, one to make a permanent record of ground motion during an earthquake. This instrument, called a duplex pendulum seismograph, recorded the shaking of the ground as a continuous squiggle on a piece of paper. It was this device that recorded the ground motion of the 1906 San Francisco earthquake. The invention of a device that could accurately measure the strength of an earthquake was a significant scientific achievement. These modern seismographs operate on the same general principles as the early pendulum instruments, but they are much more sensitive. Not only do they record vibrations, but they can be used to measure earthquake strength and duration, and also to determine the location of the earthquake almost immediately.
In 1935, California geophysicist Charles Richter combined the measure of ground motion with the distance from the earthquake's epicenter to yield a value representing the total amount of energy released during an earthquake. He called this the magnitude of the quake. The scale that Richter devised runs from magnitude -2 to infinity, although seismologists believe that rocks can at most only store elastic energy equivalent to magnitude 9 before they snap. The smallest tremors that can be discerned by humans, feeling like the rumbling of a passing train, measure around 2.5 on the Richter scale. A magnitude of 4 is equivalent to the amount of energy released by 1,000 tons of explosives. A magnitude just above 8 represents about as much energy as produced by 200 1-megaton nuclear bombs. The reason for the huge jumps in energy between one unit and the next on the Richter scale is that each unit of magnitude increases logarithmically by a factor of just over 30 times more energy released.
For example, a magnitude 5 earthquake releases about 1/30th of the energy of a magnitude 6 earthquake. So to compare a magnitude 5 earthquake with the magnitude 7.1 Loma Prieta earthquake, there's a factor of about 900 in terms of the energy release between those two earthquakes. Small earthquakes really are insignificant in terms of the release of strain on the fault that is the cause of large damaging earthquakes. Small earthquakes really tell you that a fault has enough stress on it to cause bigger earthquakes.
One of the highest magnitude earthquakes ever recorded occurred in 1964 in Alaska. It registered 8.6 on the Richter scale. Fortunately, very large earthquakes are rare. Of the thousands of quakes that occur worldwide each year, only 100 or so are strong enough to destroy human life and property. And only 1 or 2 produce major geological changes. The most obvious effect of an earthquake is just that. The earth quakes and trembles. There are many different types of ground vibrations. The rapid vibrations of the primary and secondary waves, and the slower rolling motion of what are called surface waves. Near the epicenter, where all these vibrations are concentrated at the same location, ground motion is similar to the complex sea surface in an ocean storm, with waves of all sizes mixed together. But the longer waves travel faster and may not die out for hundreds of kilometers. The amount of time it takes 2 successive wave crests to pass a stationary point is called the wave's period. For longer seismic waves, this period may be several seconds. Other materials, including buildings, have a period associated with them. In a strong gust of wind, a skyscraper will flex and bend. The time it takes for the skyscraper to oscillate back and forth once is called its natural period. When the period of a seismic wave matches the natural period of a building, the seismic energy is simply added to the oscillation of the building, wave after wave. As a result, the swaying of the building increases dramatically. Other buildings of different heights will not be similarly affected because their natural periods are different. An example of this type of amplification occurs when a child is pushed on a swing. A gentle push in time with the swing's natural period sends the swing higher and higher. In the 1985 Mexican earthquake, seismic surface wave periods matched the natural periods of Mexico City buildings between 10 and 14 stories high. Structures in this size range were seriously damaged. Given the destructive power of many earthquakes, geologists hope to develop the ability to forecast quakes in time to warn any people who might be in danger. But to do this requires a better understanding of earthquake behavior. One pastoral stretch of the San Andreas Fault near Parkfield, California, has been especially prone to earthquakes. Since 1857, residents of this area have been jolted by moderately strong earthquakes on an average of once every 21 to 22 years. Besides recurring at fairly regular intervals, Parkfield earthquakes also resemble one another in their magnitudes, lengths of fault rupture, and epicenter locations. For this reason, the Parkfield area seems like an ideal setting for an earthquake research project. Geophysicists are using a sophisticated array of devices to closely monitor the rocks along the fault. The goal is to spot any changes that might signal an impending earthquake. Evelyn Roloffs is the chief scientist overseeing the Parkfield earthquake prediction experiment.
The Parkfield experiment has 3 goals. One goal is to try to issue a short-term prediction of the Parkfield earthquake, and that would, if successful, be the first time we've ever done something like that in this country. The second goal is to record the details of the earthquake generation process in as much detail as possible. And the third goal is to take advantage of the fact that we'll have a moderate earthquake to record some of the effects of the earthquake, such as the amount of shaking that occur at different distances from the fault.
One of the most fundamental aspects of the Parkfield experiment focuses on the structure of the San Andreas Fault itself. To learn more about this structure, geophysicists have set up the Vibroseis project. At the heart of this effort is a specially equipped truck that shakes the ground, triggering waves of seismic energy. Radiating into the earth, the seismic waves move at different velocities through different rock types. Analysis of the velocity changes makes it possible to unravel the intricacies of the subsurface geologic structure.
As the waves penetrate the earth, they are reflected and refracted off the various rock layers. And by measuring first the direct wave which travels directly from the source to receivers, we can get the velocity of the rocks. And then by looking at the later arriving reflected and refracted scattered waves, we can see possibly where the structure changes and where the layering beneath the earth is.
With an understanding of the geologic structure of the fault zone, geophysicists set up other experiments to measure movement along the fault. One device that can detect movement in a very specific localized area is called a creep meter. Each creep meter consists of a wire stretched across the fault between 2 fixed points. Whenever the fault slips, the length of wire between the 2 points changes, recording the amount of motion along the fault. Although the creep meter only covers about a 10-meter zone, it runs at very high sensitivity and continuously monitors any fault motion at the surface. To derive the same kinds of information as provided by a creep meter, but over a wider area, geophysicists use what's known as an alignment array. This involves setting up markers, then conducting surveys across the San Andreas Fault to determine the local slip rate, the width of the slip zones, and patterns of deformation near the fault trace.
180 degrees, 11 minutes, 3.0 seconds.
ES2, 180 degrees, 24 minutes.
The alignment array surveys are also useful in helping scientists determine the best places to install creep meters.
The alignment array is similar to the creep meter in that it's measuring fault slip right at the surface trace. However, the creep meter is a continuous monitoring device for the center of that slip area, whereas the alignment array goes much farther away from the fault to be sure that we're not missing some important slip on auxiliary fractures out to the side. The alignment array, of course, is we only get data when we make surveys, whereas the creep meter can be run continuously, and we can look at that every day to see how much the center of this zone has actually moved.
Another important component in the Parkfield effort to better understand the mechanics of faulting is the geotometer. This shoots rays of laser light at 18 reflectors set up like the spokes of a wheel on the hills around Parkfield.
We put reflectors at different points around the valley, and we take measurements to those. So we keep track of how long it takes that light to go out to that reflector and come back with some sophisticated equipment and the computers. And by knowing how fast the light travels and knowing how long it took it to get there and get back, we can calculate a measurement to within a fraction of a millimeter on a 9-kilometer line when the conditions are really good.
This network of light is so sensitive that it can detect the slightest bending of rocks along the fault zone. The geotometer system covers a much broader area than either a creep meter or an alignment array survey.
They're all designed to look at the same kind of thing with different sensitivities and at different scales, so they all contribute to an understanding of the mechanics of the faulting.
Before the next Parkfield earthquake, scientists hope to see an acceleration of the slip that occurs on the San Andreas Fault between earthquakes. If that acceleration takes place at the surface, it can be detected directly by a creep meter. But geologists must use other techniques to detect deep movement along the fault that does not appear as slip at the surface. As stress accumulates in the earth, groundwater will respond by rising or falling. This can be measured in water wells that have been installed by members of the Parkfield research team.
Holding 65.
A sudden drop in water level, for example, is sometimes observed as the ground swells and cracks in the days preceding an earthquake. Seismologists studying Parkfield are also interested in measuring foreshocks, the seismic activity that precedes an earthquake. To do this requires a detailed network of seismometers, which the Parkfield team has set up. Tiny earthquakes are common occurrences along most active faults. But shortly before a large quake, the frequency and distribution of small shocks may change.
Being the person who looks at the seismicity, I'm expecting to see some changes in the patterns of the earthquake. The earthquakes occur in the fault zone in a fairly complicated manner. Some places the activity is shallow, some places the activity is deep. As we get more detailed information about the fault zone, we see certain knots or clusters that are active. What we're expecting to see is that the larger earthquakes will start magnitude 2s, 2.5, 3s, and they'll start migrating down the fault zone towards the area that will fail first in that earthquake. This is the pattern that's been seen in 34 and in 66, and that we're keeping a very close eye on the activity to see if that kind of activity occurs again.
In the case of the Parkfield experiment, the data obtained in the field are then regularly transmitted by satellite to the U.S. Geological Survey in Menlo Park, California, for analysis. Here, the data are monitored by scientists for any unusual activity. Depending on the extent of such activity, the Parkfield research team may declare any one of 4 prearranged alert levels.
Could you fill us in on how these earthquakes?
These alert levels indicate the probability of a sizable earthquake occurring at Parkfield within the following 72 hours.
The seismic activity for the past 2 days is shown here, and what we have are some earthquakes that represent an increase in the action. going on. These earthquakes are located here at the north.
If and when there is a high-level alert, the USGS will inform the California Office of Emergency Services, which will then issue a warning to the public.
Real earthquakes with that mechanism.
This warning signifies that the seismologists at the USGS in Menlo Park believe there is at least a 30% chance a magnitude 6 or higher earthquake will occur in Parkfield during the next 72 hours. There are no guarantees, of course, that the Parkfield research team will be able to predict the next sizable quake in that region in time to issue a warning. But members of the Parkfield team believe that their project is valuable, even if a short-term warning is not issued.
It's enabling us to record the details of fault slip to a degree that they've never been recorded before. And if there are precursors recorded by instruments that aren't involved in the alert level scheme, we'll be able to detect them after the fact, and then maybe we can use them to issue a prediction of the next moderate earthquake in California.
In the meantime, the data recording devices at Parkfield and the scientists at Menlo Park maintain their seismic vigil.
Along the San Andreas Fault and on active faults all over the world, blocks of the Earth's crust continuously try to slide past one another. This causes the rocks in the fault zone to bend and deform, accumulating tremendous tectonic stress in the process. Eventually, this massive store of energy will exceed the breaking strength of the rocks, triggering an earthquake. There's no doubt that this will occur. The principal questions are when and how strong the resulting earthquake will be. While earthquake research continues, the hopes of a reliable short-term forecasting system are still probably decades away. This task is complicated by the fact that each fault is unique, and successive earthquakes on a given fault can vary considerably. In the meantime, there are tangible steps that we can take to prepare ourselves for the earthquakes that will surely occur. Nature has forced us to live with these sudden releases of energy, but knowledge gives us the power and the chance to survive them.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.